Okay, so today's lecture will be about adders and decoders. So what are adders and what are decoders? So that's we expect to see. There is something called binary adders, which is we are using this in computer system to make the addition. Let's recall when we talk about the binary systems and we talked about addition, subtraction, we talked about two's complements and signed integer, etc. So how can I build a circuits to add some binaries? So there is a built-in function, or there is an IC, it's called adders, that do this addition, and we can use it for subtraction as well. It's called adders. So adders is very important in computer system. We can add binary digits. So we can sometimes also generate carry if necessary, because sometimes there will be a carry bits. And we can consider the carry from the previous bits. So binary adders, we can use it, for example, 16 bits binary adders, or we can use 1 bits binary adders. So it's up to the function. So most likely we have two types. We have half adders, we have full adders. So half adders, most likely when we add 2 bits together. Full adders when we add 3 bits. Okay? So what's this adder? How will it be? Binary half adder. Half adders, we said it's for something for 2 bits, right? How can I add 2 bits? Let's assume I have bit x and y. What are the possibilities of x and possibilities of y? Can be 0 plus 0, right? 0 plus 0, 0. And the carry, 0, right? What's the other option? 0 and 1. 0 plus 1, 1. And the carry, 0. 1 plus 0, 1. And the carry, 0. 1 plus 1, 10. The carry is 1. So I'm going to call these options as sum or S, and these carries carry as C. So I make a truth table, and instead of representing this in here, I'm making a truth table. So it's going to be x and y. So 0 plus 0, 0, carry is 0. 0 plus 1, 1, carry is 0, and so on. 1 plus 1, 10. 0, the carry is 1. That's how we figure out. Understood? Is that clear? So we have something related to carry, something related to sum. How can we implement this in real life? We can make a kernel maps to do this C, kernel maps for S, and we can do some another stuff. But it's actually, we realize this is the half adder, x and y, and the output which is S and C. So we realize that x and y, S will be x prime y plus xy prime, or we can say x exclusive OR with y, and C equal x plus y. So we have this representation using exclusive OR. This is what's inside the box, inside the half adder. Inside half adder. Half adder I will denote it by H, A. H for half, A for adder. So instead of doing this circuits, we're going to use this one as a shortcut, because half adder now it will be more easier for us. We're trying to make a chip or an IC, integrated chip. So this is the IC for the half adder. There's another representation, which is this. This is also inside the box. When you do the kernel maps, you will get this and this. But when you do algebra, exclusive OR, this one. So either representations are fine. This is what's inside the box. But we can make a shortcut, which is this half adder. Okay? And with this case, if someone say, this is an AND OR, can you make it NAND? Yes, we can make it. Can you make it NOR? We can make it, right? We already I've taken the first exam, so I think everyone should be familiar with this. So this is the half adder. The half adder, we have x and y, which is 2 bits. How about the full adder? the full adder will be about 3 bits. So for this 3 bits, which is basically I have x, y, z, I want to add them all of them together. So we can say 0 plus 0 plus 0, 0, and the carry is 0. 0 plus 1, for example, plus 1, we have 10. 0, the carry 1 is 1. Then, for example, I have 1 plus 1 plus 1, which is 1 plus 1, 10 plus 1, 11, 1, and carry out 1, and so on. So, instead of doing this, representing this like this way, we can make it as a truth table. So 0 plus 0 plus 0, 0, carry 0. Then 1 plus 1 plus 1, 11, 1, the carry is 1, and so on. Okay, so does everyone understand how to make the adders? It's just so simple. It's just applications of what we learned before. Application. So how do we implement this? Full adder, FA, sometimes we call it as a shortcut, FA. And most likely it's used because it's very useful because I can add 3 bits, not 2 bits. So we have the symbol for this full adders. X, Y, I have Z, I have S, and X, I have 2 outputs. Those are 3 inputs. 3 inputs, 2 outputs. Or in kernel maps, or in truth table, we can see this easy. Now, how can we implement this into kernel maps? Since we have C and S, we can do the kernel maps. Let's assume it's one example, one question of the exams. How can we make this into the kernel maps? Which is, I have the midterms. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8. For the sum bits, which will be located at 1, 2, at 1, 2, I'm sorry, it's 3, 4, 5, 6, 7. At 1 and 2, 4, 7. Here is 1, 2, 4, 7. While for the carry bits, located at 3, 5, 6, 7. 3, 5, 6, 7. Now, can we make a shortcut here? Can we make loops? I'm sorry. In this sum bits? No. Let's take each bit alone. So it's going to be x prime, y prime, z plus x prime, y, z prime plus x, y, z prime plus x, y, z. While for C, can we make a shortcut? Like 2 loops? Yes. We can make a loop here. We can make a loop here. And we can make a loop here. So it's going to be xy plus xz plus yz. I think everyone should know how to do that. We just taken exam number 1. And we need to know how to do kernel maps and designs. Okay? There is another representation of the full adders using exclusive OR. Some will be exclusive OR with Z and with exclusive OR of X and Y. And carry bits will be XY plus exclusive OR Y, X plus Y plus Z. You don't need to memorize those. There is another implementation. You can write them into your note sheets if you need. Okay? But for the quiz, you don't need to memorize those. They will be given to you if there's you need to know this representation. Okay, so you don't need to memorize this. So this is alternate way to implement the full adders. It's just for your information. So how can so the binary adders, most likely we can use full adders, or we can use, we call it the half adders. So let's assume we have 4 bits. 4 bits, 2 variables. Which means I'm going to assume that I have x and y. I have x3, x2, x1, x0, y3, y2, y1, y0. I have this. How can I make my adders? Is there a way to make it? Okay. Let's see. We need to add x and y. X0 and y0. Add each bits individual, right? So I'm going to say x0 plus y0. So is it okay to use half adders? Yes? So it will going to be something. Let me call it f0. But here I have only 2 bits. And I have f0, or I have, we call it sum and carry, s0, and I have a carry 0, right? So let me say this x3, x2, x1, x0, y3, y2, y1, y0. So it's going to be, add those. I will get sum and carry, right? How about the next bits? x1 plus y1, but I need to use a carry, right? So the half adder is not a good option, because the half adder can work with only 2 bits. Here I have the carry bits. I need to add the carry bits. What should I do with this carry bits? I need to use full adders because I have 3 bits. So here's going to be S1, carry 2, S2, carry 3, S3. So I'm going to use full adders because 2 bits is not a good option as we saw here. So let's have this example, assuming A equal 1, 0, 0, 1, 1, 0, 0, 1, 1, 1. So by making this addition, 1 plus 1, we will get sum 0, carry 1. Then the carry will be here. 1 plus 1, 10 plus the carry, 11. And so on. 1 plus 0, 0, 1, the carry is 0. 1 plus 1, 0, the carry is 0. So we got, by ending having 3 variables. Or actually, it's 2 variables, but the 3rd variable is because of the carry bits. How can we represent this into full adders? How will it be? So we can say this is full adders. Here is B0. Here is A0. I'm going to add them. And the output will be, here is the carry bits, and here is the sum, S0. Now, how about the other bits? I'm going to make it like that. Here is full adder. Here is A1, B1. Here is sum 0. And I'm letting carry 1 go into the full adders. Then we have here a carry. Here is S1, I'm sorry. Here is carry 2. Full adder. Here is B2, A2. Then here is C3. Here is S2. Then full adder. Then we'll have A3, B3, S3, and here is C4. That's it. But my answer is still not accurate 100%. Why? Because full adder, this full adder should have 3 inputs, but I wrote only 2 inputs. So there should be C0 inputs. So what's this input will be? What do you think?
0.
0. Right. That's it. This is 4 bits or 4 bits binary adders. It's called 4 bits binary adders. Any questions about this? So this is the same as what's shown in the notes. Exactly the same. But I wrote it here just to explain in details how was it. Now, can we make addition and subtraction at the same time? Which means I have A plus B, or I need to make A minus B. How can I make this subtraction? The subtraction can be done by saying I can make it as A plus B bar. Is that right? With A plus B bar, this is subtraction. Now, how can I implement this? This has been implemented using this, which is the same as 4 bits that I wrote before, But I add an exclusive OR for B because the B, the only difference coming into this side. So the only change is here. So how can I make this change? Why did I make an exclusive OR and add a bits is called M? Because we know B exclusive OR with M is equal to what? B M bar plus B bar M. Okay, so what's the point of that? When M equal to 0, then enable addition. So when M equal to 0, this will make B exclusive OR with M will be M 0 B 0 prime 0 prime 1 B prime times 0 0. So we'll end up having B. When M equal to 1, enable subtraction, which means B exclusive OR with M bar 1 bar or 1 inverter of 1 0. So B times 0 B 0. B bar times 1 B bar. That's it. So the exclusive OR here plays an important role by adding the by making the addition or by making subtraction or division. But we need to know to add something called M, which is called the control or the control mode or control signal. So if M is 0, then apply addition. If M is 1, apply subtraction. That's how some of the chips that we are using right now in our real life, that's how we apply it. Addition and subtraction can support both. V here is overflow. You don't need to worry about this, so you can neglect the overflow because I haven't covered the overflow in this class. You will see also BCD adders. This is not included. I want to make the course easier, so just erase this BC adder. And this also BCD adder circuit, also erase this. Now, binary multiplication. How can I apply? Can I multiplications using that? Let's assume the same as multiplications that we know before in lecture 1 or lecture 2, 11 times 13, that's how we apply the multiplications. Then by looking and observing, we will see that we have 4 bits times 4 bits. We'll end up having addition. Here is 1. So we'll end up having 1, 2, 3, 4. We are adding 4 bits, right? So we are adding 4 bits at the end. This multiplication becomes addition. I converted the multiplications to be addition, right? Is that clear? So for this, since I'm adding 4 bits, half adder is not a good option, right? Because half adder I'm adding 2 bits. Full adder is adding 3 bits. It's not a good option as well. So what should I do? There is we call it a modification, or there's something that we can use. It's called 4 bits adder, which will be 4 bits adder like this. This makes the problem easier. So with 4 bits adder. Now, let's try to make it more simpler. How about 2 bits times 2 bits? How can I make this multiplication using the adders? I have B has 2 bits, A has 2 bits. How can I make the multiplication? A0 times B0. A0, B0, right? A0 times B1. A0, B1, right? Then leave this one empty. A1 times B0. A1, B0, right? A1 times B1. A1, B1. Now, let's do the addition. So it's going to be this one. I'm going to call it C0, C1, C2. So, based on that, we will say that this is C0, C1, C0 equal to A0, B0. C1 equals to A0, B1. plus A1, B0, right? Then C3 equal to A1, B1, right? And there's something else. How about when I add this C1, when I add A0 plus B0? Do you think there might be a carry outs? There might be a carry outs. So plus the carry bit we can then, right? The carry bits. So in this case, we realize that C0 we can find it easy, right? Which is A0 times B0. So this is C0. So it's going to be A0 times B0. Here is A0, here is B0. Then add AND gates. Is this clear? How about C1? For C1, it's A0 times B1 plus A1 times B0. So A0 times B1. Here is A0 and B1. We can add, make this gates. So then we will make it going as inputs. Then A1 times B0. A1, B0. Then this is the second input, right? Half adder can handle second input, 2 inputs, right? We don't need a full adder because we have only 2 inputs. So the output of the adders is, this is C1 that we need, and this is the carry, right? How about C2? I'm sorry. For C2, we have A1, B1. Here is A1, B1. Okay, and we have the carry. Don't forget the carry bits. Then half adder is enough. I don't need a third one. I don't need a full adder. So we have C2, which is the carry, which is the output, and we have a carry. This one a carry. A carry out, but we don't need a carry out. But even if there's any adders, there should be a carry out bits. So then C1, C0, C1, C2 can be done. So I can say, this is my circuit that I'm going to build. So this circuit can make any multiplication of 2 by 2 bits. 2 bits times 2 bits. So I can build this hardware. I can make it into the lab by using half adders and some AND gates. Then problem done. I can make any multiplication in hardware. I'm not sure if you will take a lab into this course. Is there any lab or digital logic course? Digital logic lab? No. Okay. So when I was undergrad, there was a lab is associated with this course. So we used to build up all of the circuits, like the adders, the decoders, encoders, multiplexers, AND gates, OR gates. So we used to build them in hardware and see how this performance will be. So we not only just apply this in numbers and see the equations. So we just apply this into hardware using some ICs to see how we can program some stuff. Okay, so that's all what you need to know about the multipliers. So I'm going to go to the next topic, which is the decoders. So what are the decoders? The decoders is an very easy way to deal with this. So which is selects one output based on the inputs. Just we need to activate one output, while the rest will not be activated. There are many types of decoders depending on the number of variables. So the decoders can be, we call it n to 2 power n variable. N to 2 power n. N inputs, 2 power n outputs. Which means when I have one variable, I should have 2 power 1, which is 2 outputs. When I have 2 variables, I should have 4. When I have 3 variables, I should have 8, and so on. 4, 16, depending on how many inputs. So let's assume we have 3 variables, x, y, z. Then we should expect to see 8 outputs. And we label them from 0 until 7, of course. We should be familiar with this. And this is something very similar to what we used to know, which is the canonical form, right? D0, D1, D2, or canonical form. When we have 3 variables, or Carnot maps, we have 8 blocks. When we have 4 variables, 16. 2 variables, 4 blocks, right? Very similar to Carnot maps. or it's very similar to canonical form. So the nice way here, when we have x, y, z, the output should be one of them. X, Y, Z, the output should be one of them, which looks like I'm converting binary to decimal. So whenever I have x, y, z equal to 1, 1, 1, this means D7 will be 1, while other D's, I'm calling it D, D0, D1, D2 until here D7. The other D's will be zeros, which means only 7 will be on. Then I can figure out, oh, my input is 7. Or here's how I can transform binary to decimal. This decoder is chip exists in the world, I see that exists, and we can apply it. Let's assume that my output is 1, 0, 0. This means D4 will be on, will be enabled. Then D4 will be on, the rest will be zeros. This is the working principle of the decoders. That's it. It just allow one output to be on, depending on what's the inputs. So let's see, this is the truth table. 1, 0, 0, 0, this is equivalent here 0, 1, 2, 3, 4, 5, 6, 7. So 0, 0, 0 equivalent to 0, then D0 will be on. The rest will be zeros. This equivalent to 1, then D1 is on. The rest will be zeros. D5, 5 will be 1. The rest are zeros. D7, 7 will be 1. The rest are zeros. Clear? That's it. Now, how it looks like inside. This is the equivalent circuit. If you make a Carnot maps for each D, you need to make a Carnot maps or make the function, we will end up having this decoder. You don't need to memorize this, but I'm just letting you know that what it looks like inside. Here, what it looks like inside the decoder. You don't need to memorize this, but just for your information. Or you don't need to write it as well. What it looks like inside the decoder. Here's what it looks like. Okay? And basically, anybody can derive this. You can derive it. You already know how to do Carnot maps. You already know how to know AND and OR gates and the other. Which is, you have this function. Actually, you don't need also a Carnot map. You can say D0 equal to X prime, Y prime, Z prime, and so on. You can apply this here. Without Carnot maps, you can apply straightforward. Okay, any questions? Now, how can we apply this into some problems, digital logic circuits, which is similar to this example. This example says, use 3 to 8 decoders to implement the following functions. Some problems in the homework, I think in the last homework, you might see one problem or two about the decoders. So, implement decoders to do these functions. Now, I don't need to use AND gates or OR gates. I want to use the decoders in doing that. So 3 by 8 decoders, which means I have 3 outputs or 3 inputs, 8 outputs, which is ABC, 3 outputs. So how can I implement this? The first step, plot the decoder. You need to plot this. You need to know how to plot this. If it's 3 or 8, 3 by 8 or 4 by 16 or 2 by 4, you need to know how to do this. So this is A, B, C, and here is 0, 1, 2, 3, 4, 5, 6, 7. Okay? Now, let's look at F1. F1 is actually like 0 plus 2 plus 7, right? D0 plus D2 plus D7. So let's go to D0. Here is D0. Here is D2. Here is D7. Right? And they are all O-ring. This is F1. That's it. Very simple. How about F2? F2, which is actually D1 plus D2 plus D5. So D1, here is D2, D5. So this is F2. How about F3? D3 plus D6 plus D7. Here is D3, D6, and D7. Here is D6, here is D7. This is F2. How about F4? D1 plus D4 plus D6 plus D7. So where is D1? Here is 1. Where is D4? Here is 4. D6, here is 6. 7. F4. That's it. So that's why I'm considered the decoder as an easy topic, easy to understand, easy to implement. I don't need to go to that complexity. I need to make Carnot maps and make that shortcut and do this. So just implement. That's this implementation. Any questions about this? Okay. Now there's an advanced feature to the decoder. How about of modifying more in the decoder? It's called advanced decoder by adding something called enable. And most likely this enable is active low. Active low enable. So what does it mean, active low? Which means if enable is 0, E equal to 0, this means there is outputs, generate outputs. If enable, if 1, disable, no output picked up. So just add additional feature. I don't want that decoder works forever. I have a switch, turn it on at any time I want to turn it on. Turn it off. But here it's the active low, which means when I turn it off, it will be turned on. Or when I make it 0, it will work. When I make it 1, it will not work. This is the opposite of what we used to do, because we used to do when it's on, make it 1. That's why we call it active low. Active low means which working only with 0, not works with 1. So for example, having 2 to 4 decoders, this is what it looks like inside with enable. Again, you don't need to memorize this, what's inside, but this for your information to understand or to let you know how this being has been derived. So this is inside the IC. So by looking at this table, if we assume all decoder is active low, not only the enable, assume decoder is active low, which means make the opposite, 0, 1, 1, 0. So the enable, when the enable is on, which means don't activate any outputs. The enable is 1, which means, which is active low, which is equivalent to off. When the enable is 1, which means this is off. Then the outputs should be off. And since I assume all of the decoder is active low, then this will be 1s, which means there is no outputs. What's the value of A and B? Don't care, it doesn't matter. What's the inputs? Then all of them should be off. How about when the enable is 0, then turn on the system. The system is on. Now I have 0, 0. 0, 0 is equivalent to 0, D0. Then in D0, which means make D0 is on, then make it 0 instead of 1. Now 1, 1 equivalent to 3, which means D3, make D3 0. So make sure that when everything is active low, we are making these zeros instead of 1s. Just reverse everything from what's supposed to be. Let's assume it's active high. Active high decoder, and enable is still active low. So what's going to be? It's going to be, here is E, A, B. Here is D0, D1, D2, D3. So when 0 enable is 1, we don't care about x and y because there is no output, then they are all will be zeros. When enable is 0, then we will care about the inputs. So it's gonna be here, since d0 this will be 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. So this is in case if the encoder is active high, but the enable is active low. Okay? How we make this chip, or how would you represent this chip? Here is A, B. The enable, we will put a bubble because it's active low. Here is 0, 1, 2, 3. How about this one if it is active high, which is this circuit, which is associated with this? How about that one if it is active low? How will it, the representation will be? Here is the enable, here is B, here is A, 0, 1, 2, 3. In this case, there should be a bubble at all of them. Why? Because it's active low. At any circuit, even if it's not given active high or active low, look at the circuits. When there's a bubble, this means active low. Understood? Let me just draw this and ask you, is this active high or active low? Is this active high or active low? This decoder. Active high or active low? Active high. But we have a bubble here. This bubble is associated with enable. That's fine. It's active high. If I add bubbles here, what will be? Active low. When I add bubbles, this means active low. Okay, it's very important to understand the difference. Okay. Now, let's implement full adders, or implement this. We have S, we have carry, 1, 2, 4, 7, 3, 5, 6, 7. And I will need to use full adders. Since there is nothing mentioned, then the default is active high, unless something mentioned else, unless I said use active low. But otherwise, the default is active high. Default, active high. Okay? How can I do this? How can I make the sum and the carry? Should be easy. What do you think, guys? You didn't actually do the truth table. 0, 1, 2. 0, 1, 2, this 3, 4, 5, 6, 7. The S equal 1 plus 2 plus 4 plus 7. Right? Is that right? So S 1, 2, 4, 7. That's it. How about C? 3 plus 5 plus 6 plus 7. 3, 5, 6, 7. Right? Any questions? Straightforward. Okay? Now, we know that we talked about when we have one variable, we have two outputs. Two variables, we have 4. 3 variables, we have 8. 4 variables, we have 16. Now, can we use 2 decoders of 3 by 8 instead of 4 by 16, can we create two 3 by 8s instead of 4 by 16? Yes, sometimes as a shortcut, sometimes I didn't have ACs of 4 by 16 or that ACs are very expensive. While 3 by 8, I already have them. So yes, I can build that. I can make two 3 by 8 better than 4 by 16. But how can I make this? Which is here in large decoders. So most likely here the enable, it's active low. Then we should make this table. So we have x, y, z. These are associated for 3 by 8. Then the fourth variable, we will add not here, and we'll add it here. So this half will work from 0 to 7, and this half will work from 8 to 15. Right? That's it. And we add inverter because sometimes we want this one operate and this part, and this one operate in this part. Any questions? Okay. It's very important to look at enable is to prevent or permit or prevent doing something, or just turn on or turn off the system. It's a control signal. So active means on, passive means off or disable or enable or disable. Sometimes some chips might have active high enable, some chips might have active low enables. But the defaults of enable is active low. Okay? So which means at 1 will be disable, at 0 will be enable. Understood? Okay. Let's see an example of active low decoders. So we have A equal 1, B equals 0, C equals 0. So what does this mean? Which output will operate? What's happening when we have in active low 1, 0, 0 is equivalent to what? 4, right? 4. This means D4 will be enabled, right? But in active low means active low. Active low 0 means enable. 1 means disabled. So this makes, when I make input 1, 0, 0, this makes D4 equal to 0, while other Ds will be 1. You need to know just this for active low. If it is active high, then D4 will be 1, all other Ds will be 0. You need to distinguish the difference between active low and active high. Okay? Does everyone understand the difference? Does everyone understand the difference between active low and active high? Okay, any questions? Okay, let's see some examples to make sure that we understand it very well. Examples on active low decoders. Now, active low. Use pi equal 2, 3, 5, or m equals 0, 1, 2, 1, 6, 7. Okay. Now, when we make the kernel maps, or the truth table, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So here, this will be 1, 1, 0, 0, 1, 0, 1, 1. Yes. 0, 1, 2, 3, 4, 5, 6, 7. How can I make active load? How can I take this from active load decoders? Let's plot the decoder. Here is C, B, A. So here is 0, 1, 2, 3, 4, 5, 6, 7. Again, it's active low. Then put a bubble. A bubble, 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 bubble. So when it was active high, We used to say f equals 0 plus 1 plus 4 plus 6 plus 7, right? When it was active high. But now we are in active low. So if we are adding this, this is what will be, this will be what? When I add 0, 1, 4, 6, 7, and I can make them with OR. This is f prime, not f. Why? Because all of these are active low, which means the output will be zeros. What should I do? Add nuts, then it's f, right? That's it. There is another representation by counting the zeros, not counting the ones. Counting the zeros. The zeros, here is product of sum 2, 3, and 5. Here is 2, 3, and 5. Now, since sum product, make them ANDs. There is another representation. Either ways are correct. Here I'm taking the zeros, but make them ANDs because I'm with product of sum. Or sum of products, but don't forget to put the nuts because it's active low again. Because active low. Any questions? Let's see another example. Use a 3 to 8 active low decoder to do this. Here is C, B, A, active low 0, 1, 2, 3, 4, 5, 6, 7. Can you solve it? Try it. There are two ways. You can use sum of products and put the nuts, or you can use product of sum. Try it and tell me about the answer. Again, it's also active low, not active high. Okay, can anybody tell me? Two, 3, and 5, right? Then make them ORing. This is F prime. Make the nuts or the inverter. This is F, right? Another way, convert this to pi, product of sum. So 0, 1, 2, 3, 4, 5, 6, 7. Then now it's going to be M, whereas here is 0, here is 1, here is 4, 6, 7. Then make them AND. This is F. Again, this is valid if and only if I'm in active low. Is that understood? Any questions? Okay. Now, let's try to go to more complicated examples. Let's see this example. Control B7 segment display using only 2 to 4 active high decoders that have active enable, high enable, active high enable E1, and active low enable E2. This means this decoder has two enables. So the decoder, this is inputs 1, inputs 2, enable 1, and enable 2 active high and active low. Since two inputs, we have 3 or 4 outputs, 0, 1, 2, 3. But we have two enables. Again, that's what I did. Input 1, input 2, enable 1, enable 2. Enable 2, I put bubble because it's active low. D0, D1, D2, D3. Now this encoder is special because it has two enables. So what should I do? How can I implement this function using this chip that I have? So most likely here I have, how many inputs do I have? 1, 2, 3, 4. 4 inputs. How many inputs do I have here? 2. So what should I do? How can I make this one handle 4? I can use multi encoders, not only one. By saying what? I can say A, oh no, A, I'm sorry, C and D. D, I'm gonna make it at input 1. C at input 2. Okay? Now we have input 1, input 2. I reserve them for C and D. So what should I do with A and B? A and B possibilities are, we can have 0, 0, 0, 1, 1, 0, 1, 1, right? So which means I can use this for chip 1, I can use this for chip 2, chip 3, chip 4. I can use this for E1, I can use this for E2. Then let's figure out that we can say E1 and E2 are what? There is one active high, this one active low. So we will want to connect B to E1. So it can be 0, and here connects A to E2. We will have 0, 0, 0, 1, 1, 0, 1, 1, right? These are the possibilities for E1, possibilities of E2. But let's recall that E1 is active high, which is the opposite of my assumption. Therefore, I'm gonna, here is E1, 0, 1, and this one is active low. So what I'm gonna say, since this one active low, I'm gonna reverse this. So what I'm gonna say, E1 will be the same as usual, which is 0, 1, 0, 1, while E2, because active low, it's going to be the opposite of this, which is 0, 1, 1, 0, 0. Okay? So I can connect this to chip 1, chip 2, chip 3, chip 4. Now, how can I implement this? I'm going to first write, here is A, B, C, D. Now I'm going to draw the chips. Chip 1, chip 2, 3, 4. Okay? Here I have two inputs, 0, 1, 0, 1, 0, 1, 0, 1. And I have enable 1, enable 2, active low. Active low, I think, with enable 2, yes. Here is enable 1, enable 2, active low. Enable 1, enable 2, active low. Here is enable 1, enable 2, active low. And we have 4 outputs, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Okay? Now we all agreed that input 1 connected to C, D, and input 2 connected to C. So D every time will go to input 0. C every time will go to input 1. Now how about B and D? Here is B, and I'm going to write D like this. Here is A, and I'm gonna write A prime like this. So we said that, let's go look at the table that I write. Chip 1 will get here E1 associated with B, E2 associated with A. E1 equal to not B. E1 to not B. E2 to A. This chip 2, both at A, B. Here is B, here is A. Chip 3, 0, 0, not B, not A. Chip 4, B, not A. So here is B, not A. Okay, I'm sorry, not A here. This. Okay? Understood? Now, after connecting those, let's implement the function. 0, 4, 5, 6, 7, 8, 9, 10. So here I'm going to say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I need to take 0, take it from the 0, 4, 5, 6, 8, 9, then ORing, this is F. That's problem done. So the idea is not in this part. In this part, 0, 1, 2, 4, that's good. But now how to connect the inputs? This is my design, how to connect the inputs. Now the last example, assuming one active high decoders. So basically, D1 will be at input 0, C will be at input 1, then we have only one enable, and it is active high. So I can say I have AB 0, 0. If I connected it to another decoder, it's gonna be D0, 0, 1, D1, 1, 0, D2, 1, 1, D3. So basically what I'm gonna do, instead of making all of these chips like that, I'm gonna make it like another decoder. So how? This is 1, 2, 3, 4. Here is 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Here I have only one enable. 1, 2, 3. Here is E1, and it's active high. And I have two inputs, 0, 1, 0, 1, 0, 1, 0, 1. So I'm going to connect C and D. That's shown here. So C will be 0, D will be 0, C will be 1, 0, 1, 0, 1, 0, 1. Now, how can I connect A and B? I add another decoder here. 0, 1, 2, 3. Here is 0, here is 1. Here is BA. And here is enable. I'm going to make it 1. So 0 will go to this enable. 1 will go to this enable. 2 will go to this enable. 3 will go to this enable. Why I did this? Because I realized the option 0 and 0 is actually D0. 0 and 1, D1. 1 and 0, D2. 1 and 1, D3. Okay? Now, I can say this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's take my function. Here, 0, 4, 5, 6, 8, 9. They are all ORing. Okay? Any questions? So that's it. This is the idea. Here is if one enable, active high. This one was 1 enable active low, 1 enable active high. Now maybe you can try it as a homework. This thing, but make it active low instead of active high. The function can all of the chip, the decoder is active low. Repeat this and try it. This will be as a homework. Okay, again, any questions? Okay, so that's it for today. Sorry.